So welcome to the lecture series, Quantum Computing Essentials Part 1, Lecture 2. So in the previous lecture, we were discussing about the physical quantities in quantum, so typically described by some wave function. And we saw that the quantum states are typically vectors, column vectors and row vectors. And the physical quantities, they can be described as observables or operators, and they are typically matrices. So in this lecture 2, we will see that how to represent several mathematical quantities. Even in classical physics, we have seen that a motion is described as, say, for example, position xt as a function of time, and you can represent, say, for example, as a function of time. This is your xt. So you need a coordinate system to represent this kind of parameters. So in quantum, when we will be try to understand the geometry and the representation of the quantum states and operators, so we need to well understand the vectors and metric spaces. So there are several spaces, the topological spaces, spaces, the metric spaces, okay, the normed linear spaces, and Banach space. So these are different kind of topological spaces, and typically we will see that our quantum states are described in a particular space system known as the Hilbert space. Hilbert space, which are some Banach space, which is a subset of Banach space, or a specialized Banach space. And with the norm, it has a particular norm, and with a complete inner product space description. So Banach space is a much more abstract space, but it is some types of Banach space which are very well defined by norm and complete inner product. Complete inner product. So Hilbert space is a complete agreement with our intuition of vector space with an arbitrary. So it must be a vector space. Means it will obey certain operations, the dot product and scale and addition operations. So we will see details about the vector space. And with an arbitrary means it may have finite or infinite dimension, infinite dimension. With finite or infinite dimension of orthogonal coordinate system. Okay. Orthogonal coordinate system. So typically we have seen to represent physical quantity in x, y, z axis, right? So which is typically known as the Euclidean system. Okay. So any vectors, any point position, say for example, it is a position r, which you can represent as some displacement towards x with I cap. some displacement along y with j cap, and some displacement along the z axis at z into k cap. But here, Hilbert space, you may have an indefinite number of orthogonal such systems, and which may be finitely defined or infinitely defined. Okay, so this is very much important here to represent your quantum state. So let us see certain example of finite dimensional Hilbert space. So finite dimensional Hilbert space are your Rn, that is the so Rn, that means if you have two quantum state, two vectors, so u and v, you can take the dot product or the inner product, and you will get a scalar quantity which will belong to the real line. You may have the set of complex number or the complex number line. So it's an n-dimensional complex n-dimensional complex vector space. So Cn, and here you can have an inner product uv, where you are multiplying u with the complex conjugate of v to get the result, which is an element of C. So these are n-dimensional vector space. So they are the finite dimensional Hilbert space as well. Okay, so you can represent as this. Okay, or H or Hn. Okay, so you may have indefinite. Okay, indefinite dimension or the infinite dimension. Infinite dimension. An example is the L square plane. Okay, the L2 plane, which is minus infinity to infinity. Or you may design a function f R2 such that the integral over f square over the R is finite, and the inner product f and g is the integral of fg, fx, gx, and dx. So there are several examples. So one example is this L square part. So so classically, we have several types of quantities like positions, xt, your velocity, x, derivative of xt, okay, ddt of xt. Your acceleration is a dynamical quantity, x double dash t. Okay, so these all are the set of variables. Okay, set of variables. So this means they have they are directly measurable. But but in they are the classical states. Okay, they are the classical states, or the classical parameters, or the quantities, classical states. And you may have a quantum state. They are the function of variables. So these are the variables, but these are the functions of variables. Functions of variables. And this typical function is related to the probability distributions of the variable. So this is related to the probability distribution of these variables. So that means there is a probability description of the variable, and they are typically known as the wave function. So which we will represent as a vector of the wave function. We can represent as vector ket psi, and which is typically follow certain rules and regulations of vector space. and any operation we perform on the skate side will follow or we can represent them in the Hilbert space H. Okay, so so we can obviously typically in classical physics we can say, for example, there is one particle and we can describe in terms of xy coordinate. So what we typically do is that we take the resolution along the x-axis, we take the resolution along y-axis if the position is r, and we try to represent so in terms of x and in terms of y, how much is the contribution towards x and towards y by taking the inner product of r with x. So if it is your certain theta, so obviously this part is your r cos theta and it is your r sine theta, right? So so what is this? This is basically your inner product of your r and x, and this is the inner product of your r and y. That we typically do. That means we take the projection onto the x-axis and the projection onto the y-axis. So similarly, in a quantum state, you can represent it in Hilbert space. That means you have indefinite number of or the infinite number of bases you can use. So so instead of x-axis and y-axis, you can have the orthonormal basis as ket E1. These are orthonormal basis ket E2. Okay, this may be your ket E3. They are equivalent of your x coordinate, y coordinate, and z coordinate. So what is their relation? And their relation is any any basis EI. If you take the dot product with any other basis EJ, your answer will be delta IJ function. That means if they are equal, you will get 1 for I equals to j, or equals to 0 otherwise. Okay, or equals to 0 otherwise. Okay, so so you can represent your obviously you can represent your vector, any typical position or the velocity or acceleration, any physical quantity you can represent in terms of your x coordinate, y coordinate. Similarly, in the quantum, you can represent in terms of basis. These all are known as basis, ket E1, E2, and E3. So so there is an associated amplitude C1, some contribution towards the basis E1. Similarly, some contribution towards E2. Similarly, you can have n number of bases, so it will be Cn and E ket n. Okay, just you need to follow one thing is that these are the probability amplitudes, so you should have all Ci squared sum for all I will be 1 to maintain the superposition principle as well as the probability law. Okay, so your probability says that in an experiment, whatever outcomes you get, the total occurrence chance of occurrence should equals to 0. Okay, sum of all chance of the occurrence should be equals to 1. So this is the probability law, and this is the superposition principle. So obviously you can represent this part as your sum of Ci Ei, right, for all I. So I may be 1 to your n. So for C1, E1, this one, C2, E2, this one, this is the summation, and it's going on, right? So so how to find this Ci part, or how to get a particular Ck coefficient? So the typical rule is you can take the dot product of your with any basis. Say for example, Ek is some basis with your wave function Chi. So if you do that, you will be getting a summation. So over all the basis J, This is, say, for example, Cj, you are taking the linear sum. So you are expanding this J in terms of this equation, and you're keeping this part as well. So it will be your Ek and Ej. Okay. So I have just interchanged the positions because it's a somehow scalar quantity. So we are putting together the vectors. Okay. So so what is happening? What is this quantity? This is this quantity delta Ij, right? So you will ultimately effectively what you will be getting. So summation over chain Cj and delta Jk. So if you multiply this to quantity, if you take the inner product, you will get delta Jk. So what will be your answer? Your answer will be Ck only, because at all other values of J and K, this quantity will be 0. So only you will have the quantity Ck. So if you take the projection of your quantum state in a particular basis, so you will get the amplitude towards that, the contribution. This is the general notions or the mathematical principle, you can say. So obviously, in order to understand this quantum state and operations on them, we need to understand vectors and matrices very well. So we are studying vectors and matrices, and so as you can now represent any quantum state, okay, in terms of your vector, okay, right? So quantum so let's see what is happening. Say suppose this is your position axis, okay, and you have certain description of your wave function at xi of x, okay. So what it typically does is that suppose you take the position at dx, okay. So this is the area, okay. So this area is the chance or the probability to get this wave function within this. So what is the probability to get this wave function xi x within the boundary dx is this area, okay. And typically now instead of this function, so you are representing this function. So suppose a particular point, this one, okay. So this point may have multiple components, and you are representing, say for example, with two bases, ket0 and ket1 are two bases, or ket e1, you can take other bases as well, e1 and e2, say for example, okay. So it has two component, obviously, this side and this side, the projected component, okay. So at many other such points, so these are infinite number of points, so you can choose some discrete number of points, and you can say that at this particular point, say this point is your at x1, the point is xi1, okay. At this point it may be xi2, at this point it may be xi3, there may be several other points, okay. So at every point, if you take the projections, we will have a different values of your say for example, at this point your wave function xi of x is the combination of your some c1 ket0 plus c2 ket1. So at the point x equals to x1, okay, at point x equals to x1. Now your xi at x equals to x2, this description will be different. Say it may be c1 some prime a different value plus c2 prime another different value, okay, ket1. So c2 ket1. Similarly at different points. So all such coefficient, the probability is becoming different, okay. Note that you cannot compute the probability at a point. The probability, because it is a continuous function, at a particular point the probability is 0. So to compute the probability, you have to take a range over x, through which if you integrate the function, you will get the probability, right? That's why we write as p of x integration into dx. So p of x, or instead you can write chi of x dx. That is the probability, and which will be actually the square of this such amplitudes. Okay, so 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 obviously you can come across that these amplitudes are changing. You can keep the basis same, but the amplitudes are changing. Now if you have two positions, so the first thing, so in a coordinate system, if you have two vectors, some r1 and r2, what we try to do is to understand what is the distance between them. Okay, so so if you have a vector, okay, say for example your 1 2 3, in classically what we know as the length is r equals to your in our childhood we have learned that it will be 1 square plus 2 square plus 3 square, right? That's the Euclidean distance we measure, right? So we can generalize this. So length of a vector, okay, length of some vector, okay, v. So I have used v. You can take some quantum state as well, ket v. These are several notations. Sometimes you will see this. This is the Dirac notation, and these are typically mathematical notations. So we will interchangeably use all such different notations here. So this is the modulus of v, which is the square root of the inner product of v with v, which is actually this is the description by inner product space, that I am not assuming that how many number of orthogonal bases is there. That's why I'm taking the inner product with itself. And what typically I'll be getting, so if v has component of v1, v2, and so on to vn number of components, where this is the vector quantity, means it may belong to your complex Cn or your real Cn. In quantum, we'll see that this is this complex Cn, and all these individual v1, v2, and vn, they are belonging to your complex scalar C or your real scalar R. Okay, so you will be getting effectively v1 square plus v2 square, so on to your vn square and whole to the power half. The exact form you are getting, right? So you have three scalars, right? 1 2 3. You are doing the square and taking the square root. Here you have scalar v1, v2, vn. You are doing the same, whole to the power half. You're taking the square and whole to the power half. Okay, so if the vector v has the length, if mod of v equals to 1, okay, that means your inner product of your v with v equals to 1. You can represent this as again as this. Okay, so same notation. So you can directly assume this is the direct notation. So then we call that this v vector as your unit vector. Unit vector. Okay. If the length is 1, means if you take all the components square and square root and the answer is coming to be 1, then you call this vector as the v vector as unit vector. Okay. Standard Euclidean, on Euclidean space, standard unit vectors are your I, j, and k. In any Hilbert space, these unit vectors can be ket e1 to ket en, and n can be a finite number or n can be an infinite number as well. So Now let us see another kind of vectors. Say, for example, your u vector is some vector, and you can sometimes represent in the polar coordinate as cos theta and sin theta component. All your sin theta, cos theta are your scalar quantities, right? So what is the ket u, the inner product of the length of u to u is your cos theta, sin theta is your column vector. Now it will be conjugate, so it will be a row vector, cos theta and sin theta. If you multiply these two, you will be getting cos square theta plus sin square theta equals to 1. So this u vector is also unit vector again. Okay, so now see that any vector v, if you divide with its length, you will get a unit vector. So just we are recapitulating this part from our childhood study. Unit vector, right? Provided this length should not be 0. I mean, v vector should not be any empty set. It should not belongs to it should not be a null set. There should be elements such that mod v not equals to 0, right? Or you should not take the elements in such a way such that this is 0. Okay, so this is important. And if any vector u and another vector v, if the inner product is 0, okay, then we will call that u vector is orthogonal. This is the part sign, orthogonal to v vector, means they are orthogonal vectors together if they are unit norm. So this is orthogonal vector, orthogonal vectors, and if their amplitude is 1 and their dot product is 0 or the inner product is 0, then we'll call it as orthonormal. Okay, orthonormal vectors. So now see that for unit vectors, u dot v, two unit vectors, say for example, so two unit vectors u dot v equals to or any other vector. So u, if you take the unit vector, so mod of u mod of v into cos theta. So if they are 1 each, so you have cos theta, and we know that cos theta has a bound. It is less or equals to 1. It cannot be greater than 1. So so combining this all things together, we know that u dot v divided by the modulus u and v, okay, equal less than equals to 1, okay, or you can have u dot v less than equals to mod u into mod v, right? Any for any vector, any two vectors u v, okay. So alternatively you can write it in ket notation also. So you can write it as well as this u and v, it is less or equals to the modulus u into modulus v, okay, or the norm u norm v, and this is known as Schwarz inequality. Schwarz inequality. Inequality. This is an important inequality in quantum theory and linear algebra. There is another inequality. That is, so if you have two vectors u and v, so if you take the addition u plus v, the norm, it will be always lesser equals to norm u plus norm v, and this is known as triangular inequality. Okay. Triangular inequality. For matrices, we'll come across another inequality, which is known as CBS inequality, Cauchy, Schwarz inequality. CBS inequality is another different inequality we'll come across later on. Okay. So obviously, any vectors is associated with a norm or a distance distance quantity, what we have shown here. Okay, so now we will see certain very basic notations and operations on matrices. Okay. So so we were discussing the formal definition will come when we'll be discussing the vector space, but at least well, some very basic things we can describe here. So typically your vector is an array, right? Maybe some column or in row format, and there are elements which are the elements in Rn or Cn, and your metric will be a particular topology where the matrix the dimension will be belonging to R some m cross n or some C m cross n, complex m cross n belonging to this particular space. So matrices, any matrix A. So in quantum we'll be seeing as operator. Okay, and it will act on certain quantum state x, and it will give us another quantum state. Say it is ket phi. Okay, so it means this operator A or the matrix A acts on the quantum state vector ket psi, and the output is another quantum state vector ket phi. Okay, so the output this kind of equations we have seen and will be seeing in many other places. So the output A ket psi is a combination and the combination is ket phi of the columns of A. Okay, columns of A. So how to solve these kinds of systems of linear system and all these things? There are column picture, row picture, there are special cases as well. So I refer everyone to read certain basic linear algebra books in this part. Say you can see Gilbert's lecture series, or read some standard good linear algebra books. So that will help us, or we can discuss in more detail, but these are very preliminary things. I assume that everyone must know this thing. So So we'll be typically looking at solving linear equations of this type, a ket x equals to ket phi, okay, or simply x equals to b. Um, so this is one vector, v is your ket phi vector, and x is your ket psi vector, and how to get this kind of settings, ket psi, because many quantum you'll get the solution, the final equation as a linear equation, and you want to know the exact coefficients. So you have to take inverse of the operator, right? So so there are standard methods in linear algebra like Gaussian methods, where we do elementary operations. You can have the Gauss-Jordan method, the several kind of architecture and the algorithms are there, and we'll be discussing one by one.